As a preparation for our study on the fundamental equation of dynamics, we will give a brief summary of the basic assumptions and the laws of dynamics. In our analysis on motion in dynamics, we concluded that material bodies have effects on the motion of other bodies. Although these external effects cannot be eliminated completely, we can reduce them, which indicates that bodies free from such effects stay at rest or hold their uniform rectilinear motion with respect to a special frame of reference, called inertial frame of reference. As a result of this assumption known as the first law of motion, the acceleration of a given body is due to the effect of other bodies, and we consider this effect as a force acting on the body. Here the ball rolling along a straight line collides a greater ball at rest and changes its course. The effect of the greater ball on the motion of the rolling ball can be represented by the force F. Based on measurements providing a quantitative description on these effects on the state of motion of bodies, we assume that the greater the force acting on the body is, the greater the acceleration and the mass of the body are. The mass of the body is a quantity which only depends on the physical properties of the given body. We establish the quantitative relation between the force F acting on the body and the acceleration a and the mass m of the body by applying the simplest possible definition, stating that the force F is equal to the product of the mass m and the acceleration a. This definition, known as the second law of motion, allows us to measure the mass and the force by applying dynamic methods, if we suppose that the same measurement apparatus exerts the same force on different bodies. The third law of motion states that the action and reaction between two bodies are equal in magnitude and opposite in direction. In other words, the force FAB exerted on the body A by the body B is equal to minus the force FBA exerted on the body B by the body A. We can recognize the importance of this law when we study the motion of systems of several bodies. The fourth law of motion assumes that forces acting in the interactions between bodies can be described by vectors. If the bodies B and C collide with the body A at the same time, then their effects on the state of motion of the body A can be represented by the forces FAB and FAC. These forces are vectors, since the result of the collision experiment shows that the net effect of the two bodies B and C can be represented by the net force equal to the vector sum of the forces FAB and FAC. The static measurement of force and mass is based on this law, where we use the fact that 2 point-like bodies stay at rest if the two forces acting on them are equal in magnitude and opposite in direction. The static measurement of mass also uses the fact that the gravitational acceleration is the same everywhere on Earth. As a result, we could establish another fundamental law of nature called equivalence principle, stating that the gravitational mass of a body measured by a weighing scale is equal to its inertial mass, which appears in the second law of motion. We can combine the second law of motion with the fourth law, where the result is called the fundamental equation of dynamics. The fundamental equation states that the product of the mass m of a point-like body and its acceleration a with respect to an inertial frame of reference is equal to the net force F acting on the body. If r is the position vector of the body with respect to a given reference point O, then this equation states that the mass m times the second-order derivative of the position vector r of the body with respect to the time t is equal to the net force F, where F is equal to the vector sum of all the forces F1, F2, ellipsis, Fn acting on the body. We can apply the fundamental equation of dynamics in two different ways in the study of motion of point-like bodies. If we observe the trajectory of a body, described by its position vector r as a function of the time t, then we can determine its acceleration a, which is the second-order derivative of the position vector r with respect to the time t. If we know the acceleration of the body, then we can determine the force F acting on the body from the equation stating that the force F is equal to the mass m of the body times its acceleration a. This kind of application of the fundamental equation is very important if we are able to find a whole class of motions, where the mathematical expression of the force related to each type of motion in the class is the same. Such a mathematical expression describing the force related to the motions of the given class is called law of force. The second way to apply the fundamental equation is to follow the opposite direction. For a given law of force, we determine the forces acting on a body, and compute the net force F by applying the parallelogram law. Then the fundamental equation will tell us that the acceleration of the body given by the second-order derivative of its position vector r is equal to the net force F divided by the mass m of the body. By integrating this equation, we can determine the position vector r of the body as a function of time, that is, we can describe the trajectory of the body during its motion. Let us consider some examples for the first way to apply the fundamental equation of dynamics. In the first example, we present the law of force for the motions of freely falling objects and projectiles. Galileo and his experiments demonstrated that the motions of bodies in free fall and projectiles belong to the same class related to the gravitational acceleration, where the law of force is the gravitational force or the weight of the bodies. This law of force can be derived from the observation of free fall or projectile motion, if the force of air resistance acting on the moving body is neglected. Galileo found that the distance s which a falling body covers in a given time is always proportional to the square of the time t measured from the beginning of the free fall. Since the body moves along a straight line, we can conclude that the speed v of the falling object is proportional to the elapsed time. Therefore its change of rate or acceleration a is constant and points downwards, in the direction of the motion. We denoted the acceleration of a body in free fall by the letter g, and called it gravitational acceleration. Then the law of force for gravity is given by the equation stating that the force F acting on a body in free fall is equal to the mass m of the body times the gravitational acceleration g. This is the law of force for projectiles with negligible air resistance as well, since the horizontal component of its motion can be described as a uniform rectilinear motion, whereas its vertical component is a free fall with the acceleration g. The second example considered here is the class of simple harmonic motions. In the study of simple harmonic motion we presented some experiments with oscillating bodies suspended from springs. The results showed that the acceleration a of a body performing such a motion is equal to minus the ratio of 4 pi squared to the square of the period t of the motion, times the displacement x of the body from its equilibrium position. If the mass of the body is m, then the law of force for the simple harmonic motion of the body states that the force F acting on the body is equal to minus m times the ratio of 4 pi squared to t squared, times x. However, the experiments applying springs also demonstrated that if the mass of the spring is negligible with respect to the mass m of the oscillating body, then a body of the mass 2 times m or 3 times m performs simple harmonic motion where the square of the periods t is also 2 times or 3 times greater than t squared measured in the original case. Therefore the factor 4 pi squared times m divided by t squared in the force law is independent from the mass m, that is the factor is constant which is completely determined by the geometry and the physical properties of the spring. As a result, we obtain a law of force stating that the force F acting on the body in the direction of its motion is equal to minus the spring constant k times the amplitude x of the oscillation. It is called the modified version of Hooke's law describing the restoring force exerted by the spring on its fixed end. In the original version of Hooke's law the force applied on the string to stretch or compress it and the negative sign is missing from the right-hand side of the law of force. The modified version of Hooke's law states that the direction of the restoring force is opposite to that of the displacement and its magnitude is directly proportional to the displacement. The general form of the law of force for quasi-elastic forces states that the magnitude of a force F directed towards a center O is proportional to the distance r of the center from the point P where the force is applied. In other words, the force F exerted by a body against deformation forces is equal to minus a constant k, times the displacement vector r pointing from the center O to the point P. The spring constant k can be determined by applying the static measurement of force. We can suspend a series of weights with different masses from the spring and measure the stretch of the spring for each weight in balance. By calculating the ratios of each weight to the length of the stretch, we obtain a series of data points on the weight versus displacement plot. If we fit a line on the measured data points in the linear regime, then its tangent will give the spring constant k. A third example for the application of the fundamental law of dynamics is related to the general motions governed by Newton's law of gravitation. Newton derived this law from empirical observations of planetary motion establishing the orbital motion of the Earth and the Moon. He applied his second and third laws of motion to explain the orbital motion of these planets, and he could deduce the universal law of gravitation. This law of force states that the magnitude of the attractive force F acting between 2 point masses m1 and m2 separated by the distance r is equal to a universal constant g, multiplied by the product of the masses m1 and m2, and divided by the square of the distance r. The force acts in the direction of the vector r joining the two bodies. The law of action and reaction also states that the bodies exert equal but opposite gravitational forces on each other. Since Newton's law of gravitation is a universal law, it can be studied in lab experiments as well, where the gravitational constant g was measured to a high precision. We have mentioned only 3 different laws of force here, but there are many other types of law of force, for example those which are related to friction or air resistance, and we can also talk about buoyant forces or the force acting between charged bodies, and so on. We have seen that the second way to apply the fundamental equation of dynamics follows the opposite direction, where we determine the motion of a body from a given law of force describing forces acting on it. For the sake of brevity, let us start with the rectilinear motion of a point-like body with respect to some frame of reference. We can attach a Cartesian coordinate system to the frame of reference such that the body travels along its x-axis, and its instantaneous position is described by its x-coordinate as a function of time. Then the fundamental equation of dynamics has only one component along the x-axis, which is the equation of motion of the body. The equation of motion states that the mass m of the body times the second-order derivative of its x-coordinate with respect to the time t is equal to the x-component of the force F acting on the body. Since the body moves along the x-axis, the y and z components of the force F must vanish. As a result, the motion of the body is completely determined by the x-component of the force. In the general case, the component Fx can depend on the position x of the body, the first-order derivative of the coordinate x with respect to the time t that is the speed of the body, and the time t itself. The equation of motion is a second-order differential equation, and we can determine the motion of a point-like body by solving an initial value problem for this equation. In other words, for a given initial value condition, that is for a given position x0 and a given velocity v0x of the body at the time t equal to 0, we solve the differential equation. By solving the equation with this initial data, we obtain the x-coordinate as a function of time describing the instantaneous position of the body along the x-axis during its motion. In the case of spatial motion, the instantaneous position of a moving point-like body is described by the position vector pointing from a reference point O representing the frame of reference to the position of the body. Then the fundamental equation of dynamics is a vector equation, stating that the mass m of the body times the second-order derivative of its position vector r with respect to the time t is equal to the force F acting on the body. In the general case, the force F depends on the position of the body, its velocity given by the first-order derivative of the position vector, and the time t. The position of a point-like body can also be described in a Cartesian coordinate system attached to a frame of reference by the coordinates x, y and z as functions of the time t. Then the equations of motion for the body can be expressed in Cartesian coordinates, stating that the mass m times the second-order derivative of the x-coordinate of the body with respect to the time is equal to the x-component of the force F acting on the body. The two other equations of motions have the same form with the components y and z of the vector equation. The components x, y and z of the force F acting on the body are functions of the coordinates, their first-order derivatives with respect to the time t, and the time t itself. The equations of motion form a system of second-order differential equations. If we want to determine the trajectory of the moving body that is its Cartesian coordinates as functions of time, we need to solve an initial value problem for this system. As an initial value condition, we have to prescribe the initial coordinates x0, y0 and z0, and the initial velocity components v0x, v0y and v0z of the body at the time t equal to 0. The initial position and velocity of the body are arbitrary initial data, which determine the unique solution for the coordinate functions x, y and z obtained by solving the system of differential equations. The fact that given forces acting on a body and the initial data of its position and velocity uniquely determine the motion of the body, is equivalent with the principle of causality in mechanics. Such a quantitative study was only allowed by the introduction of the concept of the force in the second law of motion stating that the force F acting on the body is equal to its mass m times its acceleration a. When we say that the acceleration of an object is produced by a net force acting on it, that is a force causes it to accelerate, it is just a simplified expression of the fact that we have to find the real causes of its acceleration in the geometric and physical state of other bodies at various distances of the object.